What's up today, guys? How are you guys doing? Today we are going to examine and practice about asymptotic notation analysis. That we have the list of problems of asymptotic notation about that it has function of Fn is in the space of notation or not of notation Gn. That's what I'm going to do today. So we have a list of problems that I am introducing today, and we are going to prove it for for the example. For the first one is theta notation that we need to prove the function fn that is n squared divided by 2 and minus by 3n is in the sense of theta notation of n squared or not. That we have to prove this one. So let me think about how can we start to prove this. To prove this, so the easiest way to prove something about asymptotic notation, you have to know what is the definition of that notation. Alright, if you know the definition of asymptotic notation, it is going to easy for you to prove it. Okay, let me show the example for this problem. For the first one, we are going to write that we want to prove that n squared divided by 2 and minus 3 multiply n is theta n squared. This is what we are going to prove. Yeah, we write on the first line and we initialize the function of fn and gn. For example, we write by Sn is n squared divided by 2 and minus 3 multiply n, and the function of Gn is n squared. That means for in other words, we want to prove that Fn is theta of n squared or not. This is what we are going to prove. And so if you know the definition of theta, you can start to prove it. So for the next thing, we are going to write the definition of theta notation. Because if we can prove that this function fn is follow the definition of theta notation, then it is a theta notation for sure. So we write by definition of theta, there exists c1, c2 is greater than 0 and n0 is greater than 0, such as this is the crucial part for the definition, that is such that c1 multiplied gn is greater than or equal to fn, and the function fn is less than or equal to a c2 a c number 2 multiplied by gn. So if you can remember the definition, you can remember by a graph that is a gn is the theta notation is a Gn is both low bound of Fn and upper bound of Fn. That is, if we write in the graph, on a graph, you can see that Fn is between for both Gn with some constant C1 and C2. So we have for sure to prove it, we have to find C1, C2 and N0. That what we are going to find. Oh, I forgot one thing. We should include that for all n is greater than n0 or equal to n0. The n0 is meaning the start point of the graph that is true. It is true for all this for all n that is greater or equal to the start point. If it is a theta notation. Okay, so for the theta notation, we are going to split to two parts. That is low bound, the low bound function and upper bound function. So for low bound, the equation is C1 Fn is greater than or equal to C constant C1 multiplied divided by Gn. And let me rephrase this as a real number, not an Fn, that is n squared divided by 2 minus Gn is greater than some constant C1 for all n greater than 0. That is C1 multiplied by Gn. Okay, I'm going to write not okay. So let me zoom in. This is our row bar. Fn is greater than or equal to C1 multiplied by Gn. Oh, sorry. This Gn is going to be n squared, right? N squared. So how can we select some constant C1 and N0? We have to find this. That's this. That this inequality will be true. We have to find it. We have to find constant C1 and N0. That is our goal. So the simple way to prove this, I have to simplify this expression as n squared minus 2 minus tn is it is so hard. So it is so hard to prove and find C1 that is true for this inequality. So what I can do is what I will try is try to merge these two equations to one, and it's going to be easy because firstly that means I have to simplify this to something that has similar expression, right? Something that has n squared. I have to rewrite this phrase as n squared. So I can merge this. I can merge two of these to one n squared. So what can I do is I say that 3n is the important part that you can prove. It is easier to random select constant if we can prove like this. So I say that 3n is less than n squared divided by 2 for all n greater. Let me see. What is the starting point that this expression? What is what is the starting point such that 3n is greater than or equal to n squared divided by 2? So for n equal to 1 is 3 divided by 2. Oh, this is false. Let me try some for other starting point. What about n um n equal to 4? 3 multiplied by 4 is 12. 4 times 4 is 4 squared is 16. 16 divided by 2 is 8. So this is also false. We can try to find the starting point n because we know that n squared is grow larger than n, right? It must have some starting point so that for all after that starting point, this inequality will be true. So what about 6? 6 3 multiplied by 6 is 18. 6 squared is 36. 36 divided by 2 is 18. So this is true. And we know that after this point, n is 7, 8, 9, 10. This inequality will always be true because the function is increasing function. And for example, if n say is equal to 7, it will be 21 is less than 49 divided by 2. This is about 24 and it will be 2. So we can say that for all n greater than or equal to 6, this expression is true. So that means I can change the equation of 3n to n squared. How can we do that? So we use the fact of inequality that 3n is greater than for all n greater than 6, right? And how can we continue this equation in equality? So we can do something like multiply both sides by -1, like I modify it by -1, it will be negative of 3 multiplied n, and the inequality when we multiply or divide it by some negative number, it will be opposite side. For for the greater than or equal to side, the side will be greater than or equal, and it will be negative of n squared by 2. And we got this equation that is similar to this one, right? Negative tn and negative tn. That is the same. So we can. So what can I do? The next thing is I can uh, merge this, add add it to both sides of inequality to make this inequality equation the same as the whole equation. So I add them is n squared divided by 2 is greater than divided by 2 minus 3n and we get the same equation on the left side. But we have found the problem that the right side is 0. That is impossible because we say that the constant c1 must be greater than 0 and Gn is n squared. So it's not exist c1 that make this right side of inequality to be 0. So this one we cannot use. So we have to use other equation like it cannot be straight n squared by divided by 2. It can be straight like that. So what about we do 3n is greater than or equal to n squared divided by 4, right? I can use divided by 2 because after that the right equality will be 0. What about we try some smaller equation like divided by 4 for all n equal what? And we have to find this starting point. This thing, the most the hardest part about this is to find to find this inequality. You have to practice them to find this inequality, and it will make your life easier. So let me write it. What about n is we know that the 6 is 2, right? But it divided by 4, so it will be more smaller. What about we can try the large n if you want. So 3 multiplied by 12 is 36. It will be greater than or equal to, sorry, it should be less than or equal to, yeah, sorry about that, because the the latest the later we will multiply by -1, the sign of inequality will be the opposite side. So n squared of 12 is 144 divided by 4. This is about 38. That is true. And we found the point starting point is n is greater than or equal to 12. After that we can write the same. We can write, oh, we know that 2n is greater than or equal to n squared divided by 4 for all n greater than 12. And we will write this all the time. And we multiply both sides by -1. The sign will be in the opposite side. So we will negative n squared divided by 4. And we try to make like this equation. So we add n squared divided by 2 3n and n squared. And we combine combine these two equations. So it will be n squared. This remain the same. This will mirror to 2n squared divided by 4, that is equal to n squared divided by 4. See, we have got both sides of inequality and the left side add the same for this left side. And the right one, we get n squared divided by 4. That is 1 divided by 4 times with n squared. This is, this is exactly the same as Gn, and this one is C1. See, we can, now we can find the constant C1 and the variable n. That is, starting point is for all n greater than or equal to 12. That means we can write, let me get a new page. We can write, okay, we can write we choose C1 equal to 12 and starting point is 12 because we say that for all n is greater than or equal to 12, this inequality will be always true. Fn thus Fn is greater than or equal to C1 Gn for n is greater than or equal to starting point n0. Or you can simply write this Fn as n squared divided by 2 minus Gn, and Gn is n squared. You can write this. You can write this also. So the next thing is upper bound. This we just done the upper bound, the lower bound. We have to do the lower bound also. And what is the upper bound? The upper bound is this one. Fn less than or equal to C constant C2 times Gn. This one will be easier than the low bound one because I will show you. So we write Fn is less than or equal to C2 Gn. And our goal is the same. Our goal is to find the constant C2 and N0, the starting point so that this inequality will be true. So let me first rewrite this as n squared divided by 2 at the n less than C2 n squared. This one will be easy because you can see that uh, n squared divided by 2 is certainly less than or equal to c constant n squared. And or you can try. That means if we can cut this expression to another form that we do at the same as lower bound, that we try to transform the equation of negative gn, we transform it to negative n squared divided by 2 or negative n squared divided by 4. We try to perform this. And why did we do that? Because after that we can combine these two equations to one expression, and we can simply say that this one is Gn. All right. The hardest part of theta is about this inequality, that you have to write this inequality. You have to practice them. So the next exercise will show that. So what about this? How can we cut this equation, and I will try to remain just this. What I can write is n squared divided by 2 or 3n. I will try to transform this equation to this one, so I can find the constant c2. I try to transform this one to this one. That is our technique. So n squared divided by 2 minus by tn is equal to n squared divided by 2 minus tn. And we know that the easiest way to cast this is we say that negative 3n is less than 0. That is the easiest, because what n? That is n is equal to 1. That means because n is equal to 1, this one will be negative and absolutely less than 0. So this equation will always be true, because this one is negative. Negative at the same time for positive integer n. And we do at the same that we try to combine this, and it will be transformed to n squared. That is, we add both sides of inequality by n squared divided by 2. That is n squared divided by 2 minus tn, and 0 we add by n squared divided by 2. So we can simply write this expression as n squared divided by 2 tn is less than n squared divided by 2. And you can write this as 1 divided by 2 n squared. And just again, it's the same expression of the definition upper bound of theta notation. See, it's the same. N squared divided by 2 minus by Tn is less than or equal to n squared divided by 2. That is, this one is constant C2. That is constant C2. And this one is N0. So we can say that thus we should C2 equal to 1 divided by 2, right? And the starting point of this upper bound is 1. So that Fn is always less than or equal to C2 of Gn. And we got our upper bound that is easier than the part of lower bound. So we can summary that, and the next step is we summary that we should C1 equal to 1 divided by 4, that is C1, and C2 is 1 divided by 2, and what is the starting point? The starting point we have two starting point. Like for upper bound we have starting point equal to 1. For lower bound we have starting point of 12. To combine both lower bound and upper bound, we choose the maximum one. So between 1 and 12, what is the greater number? It's 12, right? So we say that starting point for both upper bound and lower bound will be 12. And we write the phrase that I am lazy to right? It is C1Gn is greater than or Fn C2Gn for all n greater than n0. Don't forget to write this part. It's the important thing for theta notation that we specify the starting point. Thus, and we say that thus the n squared divided by 2 in a 3n is equal. We can use the sign of equal, but in the reality we have to say that n squared divided by 2 minus tn is in the set of theta notation of n squared. And that's the end of the first problem. So we can prove this. So let me remind you how to prove the theta notation again. So the first thing is, you have to know the definition of theta notation, and it is the lower bound and upper bound. And when we try, the hardest part when we try to find the constant c and starting point, that is the crucial one and the hardest one to find the inequality equation. Like, so I have to try to simplify this n squared divided by 2 minus 3n to simplify, but we need to simplify it to n squared. That's what we are going to do. And we do the same for the lower bound as upper bound, just swap the sides, and the observation that the negative 2n is always less than or equal to 0, because the right one doesn't have 3n, like we can cut it out, right? That was the thing you need to do. Okay, so for the next problem is function fn is 6n cubed in power of 3, and the gn is n squared. We need to prove that fn is theta gn or not. So what we can do, we can write that we want to prove that fn equal to 6n power of 3 is theta of gn equal to n squared. The first line we obey specify the goal what we are going to do for this problem. We want to prove that fn is a theta of gn. That's, and and the next thing is, okay, so we are going to prove that for theta notation. So we say that by definition, let me write by hand. Oh, and we can write it by hand. That is the axis c1 and c2 that is greater than 0, and then the starting point, positive number starting point, so that so that we write the definition of it as c1 gn is greater than or equal to fn, and c2 gn. That is the same for the previous problem, and we are going to do it the same for the first one, that is the lower bound and upper bound. For the rule bound, or we can the first line we can specify that is true or not, right? This equation is true or not. We want to prove this. What we can write. So for the row bound, it is uh, the function fn is 6n power of 3 is greater than or equal to c1n squared. And we need to prove this. So it's not the same as the first problem that we have some equation that is complex, like it had the trash one that is negative tn, that is the x is z, and we cannot simply write for the n square. Then that is our hardest part. But what about this equation? How can we transform n power of 3 to n square? It is an any way to transform this. Well, actually it cannot, right? Because n power of 3 is grow farther and go larger than n square. If I um, plot, plot the graph on the decimal graphing, and I say that x square, and right, we can see that the graph of n power of 3 is go larger than n square. See, it go much better. So we for this problem we try to limit the c1 to be alone. So what I mean is we try to leave the constant c1 to be alone and no one attached to each. So what I do is divided by n square for both sides, right? So what I do is n power 3 divided by n square, and this one will be constant c1 constant c n square divided by n square. I can cut this one, and this will be 6n, right? So that means we have to find the constancy that make this equation to be true. Actually, actually for this one we can, sorry, we can write just we can just write like this. So we know that n power of 3 is much larger than for n square because the power that number it is 3 and 2. It will be go larger, so we can say that 6n power 3 is greater than n square for all n equal to 1. greater than or equal to 1. This is the starting point, and this one is 1, the constant C1. So this is C1, right? How can we know this? It's easy to see that because I show you in this small graph that n power of 3 is grow larger than n square. So it's easy to say that from n equal to 1, this inequality equation will be true, right? So now we can we can write this and choose C1 is equal to 1 and the starting point is 1. We can shortly write this and summary later. So for the next thing is upper bound. Now we prove the lower bound. Next we have to prove upper bound. So for the upper bound, we write the fn function, right? Fn function that is 6n power of 3 is greater than or equal to constant c2 n squared. So here is the problem. Just the previous one, we know that n power of 3 is go larger than n squared. How can it go the n power of 3? How can it go less than n squared? That is the problem we found. So we know we we look we look on it by the eye and we know that this equation, this inequality equation cannot be true. We need to show it in the mathematic term. So how can we do that? So we can leave the c constant c2 alone again. So I try to divide it both sides by n square, right? Because I want to cut out n square. So we write uh, c2 constant c2 divided by n square, and we cut out this one, and we left this constant c2 alone, and it will be 6n is less than or equal to c2. So, and I swipe the side because I want I want to find the constant c2, some constant c2, and it will look much easier. So now we got this inequality equation. We say that C2, constant C2, must greater than or equal to 6n. How can it's possible? Because how can it be possible? Actually, this equation is impossible, and I will show you. We know that C2 is constant, right? It must be constant value. It's fixed value, not the variable. What about n? The variable n is variable. It can be so much large. It can be arbitrarily large. What I mean, like n it can be 1 million or 1 billion or 1 trillion. So that means the constant C2 is dependent on the right side of the n, and we can show that this this one we cannot find the constant C2, so that for all this inequality at some starting point it will be true. We can write something like this. Since n can be arbitrarily large, the arbitrary means it can be any value that is large. It can be any value, 1 billion, 1 trillion, that as I said, it can be so much large. We cannot find constant c c2 because if I choose some constant c2 like 100, if I choose let me say that, oh, I will choose c2 is equal to 100. This equation will be true for all n starting point or not. What if n is 100 also? It will be 600 and equation will be false, right? See? And if I let c constant c2 is equal to 1000, what about I let n is equal to 1000? This equation will be 6000. 1000 is less than 6000, so this one is also false. That's why we can say that n is arbitrarily large and we cannot find constant c2. And then we can just say that we cannot find constant c2 such that six n power t is less than or equal to c2n squared. Thus, 6n of 3 equal to theta of n squared is false. This is our summary for the false one. We can just simplify that, or from the proof that we want to prove is true or not, and the summary we say that, oh, this one is false. It can be true because we prove it, right? So that how can prove the theta notation. So let's go to the next problem. So this one is Fn is secn secn uh, at and plus 10 secn plus by 10 and Jn is n square. We want to show that Fn is Fn is little o. Wow, it is not theta notation. The little o notation will be much easier to prove for a symbolic notation, honestly, because we can use some limit equation to prove it. I will show you, and I think it's the easiest way that we can prove like this. So at the same, to prove it, we have to know the definition of little o, and we can say that we want to prove that we want to prove that Fn equal to 6n plus 10 is uh, little o of Gn of n squared. So little o is likely the same as big O, right? Big O is the upper bound of some function, but little o is more strict, right? So we write that by we can the first method we can say that it is the first method that you can check with it. Uh, the theory say that for the limit n is near as infinity of Fn Gn if it's equal to 0, then Fn equal to little o Gn. And yes, this is the first method. We just use limit function and prove it that Fn divided by Gn is of the limits n is infinity is equal to 0. Then Fn is the listen O of Gn. So we can check it that limit n be as nearly as infinity. Fn is 6 n plus 10 divided by n squared. So for the limit definition, the the numerator is n power of 1, right? And denominator is n squared. The denominator is cubed, is go larger than this one. So we can write it equal to 0. And since this equal to 0, we can just summary that thus 6n plus 10 is equal to little o of n squared. And that is for this problem. For the second method, we can write the definition of little o. We say that by definition for all constant c greater than 0, there exists some the starting point n0 is greater than 0 such that Fn is less than Cgn for all n is greater than starting point. This is the definition of little o notation. So what we are going to prove is Fn, right? We have to write that 6n plus 10 is greater than Cn squared for all n greater than or equal to starting point. We have we have to find the constant c again. So how can we do this? So what can we do? The the definition is different from theta notation, right? You can see that the different keyword is for all c. The theta notation will be for sum. We just need to find for sum. But for little o notation, it's for all. That means for all constant c that is greater than 0, there will be some starting point so that this inequality will be true. So what can we do? We can write something that the little o, if we don't use the limit method, is going to be hard for this one to prove, but I will try. So so for the constancy for all c, there must exist some the variable n, right? I will think as the easier the way that we can prove this equation in the easy manner. Mm, I think what we can do, we can we can do the same thing for the theta notation, that we try to transform this equation to this equation. The n must be m squared, right? But the easy way to prove this, we for all c, right? For all c. There must exist n0. Oh, and the derivation is uh 0. We must uh for the for this equation, we have to find n is greater than for something, for constant c. We have to write this equation. So let me think of how can we write this one. Actually, we just prove this by the limit method, and it is the easiest way to prove this. But if you want to prove this one, we can, I think we can write some the thing that's about a plus b square is equal to a square plus 2ab plus b square. We can use this one to this one. So what we are going to do, we write 2 3 and write a t square plus 1 present or equal to cn square. So this what I'm going to write. But we have to find this. So in order to do that, remove this sign, it should be only less than is the correct one. So what can we do? We can again we can uh, try to combine these two equations to the same one. We can write as 10 is less than or equal to 10n, right? And for all n is the starting point, it should be 1. This one is constant, but this one will be the increasing function, that is for n the positive integer n greater than or equal to 1. This one will be 10, 20, 30. It will be it's always be true. So after that, we write this one. We can write 6n plus 10 is less than. We add the 6n both sides. We add 6n both sides, and it should be. And we combine these two equations to 16n, right? And the next thing we have, what we have to prove is um, then this one is less than, much less than cn squared. This one we want to prove that 16n is less than cn squared also less than n squared. So it's easy to see that we divide by um, we try to isolate the n to be alone. We divided by n both sides, and we write that is 16 is less than cn, and we try to left n alone to be alone, and n is 16 divided by c, and so we can isolate n, and we got this inequality equation, that is n is greater than 16 divided by the constant c. That means, what is that mean for? That means for all constant c, that is c is greater than 0, we can find some constant, find the positive integer n, that n is also greater than 0. If we can prove that we can always find n for some constant c that is greater than 0, then the reason O will be true. So how can we do this? That means, and don't forget that we can we can say that we can choose n0 equal to maximum is 1 and um, plus 1. That's what we can do. And what and that means for any constant c, we can uh, find the starting point that is greater than 16 divided by c, and nc and n0 must be the integer number, so sometimes it can be 0, so we use the maximum function to be 1. So how can we write after this? So we can say that sin is less than 16n, right? And 16n is less than cn squared. For all c constant c is greater than 0, and for some n0, and we say that it's equal to make 1 16 divided by constant c plus 1. Thus 6n plus 10 is less than cn squared for all constant c greater than 0. And we can summary that 6n plus 10 is equal to little o of n squared is 2. And we end our proof. For the next one is, if you don't like how to prove like this, you can use that the first method that we prove that its limit. The limit is equal to 0. We can summary that fn is little o of gn. That is the easiest method to verify the little o notation. So for the next form is this one. For this one, fn is 7n squared and gn is n power of 3, and we have to prove this. Prove that fn is theta of gn, and we write at the same that for the first problem and second problem. We can write that we want to prove that fn is equal to theta of gn is 2 or not. And we can specify that fn is equal to 7n squared and gn is equal to n power of 3. And the next thing, we just specify the definition of theta notation. We say that by definition, there exists some then c1 and c2 is greater than 0, and the starting point n0 is greater than 0, such that c1 times gn is n power of 3 is less than or equal to fn, and fn is 7n squared less than c constant c2 n power of 3. And we do at the same as the first problem and second problem, that is, the first is lower bound, right? We have to find the constant of c and the starting point. So for the lower bound is c1 n power of 3 less than or equal to 7n squared. We have to prove this, or we write on the other side. Another side is 7n squared is greater than or equal to c1 n power of 3. Don't forget to specify the starting point. This is the lower bound, and we find the problem at the same as second problem, right? That we know that n squared can can be go larger than n power of 3, and we can prove we can contradict it that left the c alone, the constant c alone. So I try to alone the constant by divided it both side by n of power of 3, and we can cut this out, and this one will be 7 divided by n. So we get that c1 is less than or equal to +1. And how can we contradict this inequality in equation? I mentioned that n is so much large. N is more than 1 trillion. The C1, the 7 divided by some large number, it will constant uh, go nearly 0, right? And C1, some some of the large n, some of the large n will be so much large so that make this side to be 0, right? So if I write the dead mode for 7 divided by x, you can see that when x is arbitrarily large, the limit is going to be 0. But we know that c1 can be 0, right? And it will be contradict with it. So what can we say? We can say that since n can be arbitrarily large, the constant c1 will be and it contradict with definition of theta notation, right? That c1 must greater than or greater than 0. But when n is so much large, we know that c1 will be equal to 0, and it's occur the contradiction of this inequality. So we can say that we just end this proof because it's occur the contradiction, and we just say that 7 n squared equal to theta n power of 3 is false. That's what we can do. Or for the other way around, you can write the n alone and say that n is greater than or equal to 7 divided by c, right? And it must be like this. N is less than or equal to 7 divided by C is in is contradiction because we need the starting point that is greater than or equal. It should it the n is should be increasing, but this inequality equation we limit that the upper bound of n can be only 7 divided by c. If it's greater than that, it will be 4. So we can find the constant c such that it have the starting point that makes this inequality to be true. So for the next problem about this, and uh, it the theta notation again. I will not write the same thing as above, and I will just write the lower bound, not the definition. So for the lower bound of this fn and gn, this one is fn is n power of 3 plus n log n, and gn is n power of 3, and we have to prove that this is theta of gn or not, and we specify the definition that we want to prove, and we prove for each section that is lower bound and upper bound. For the lower bound, that is we have to find the constant c1 of some starting point, right? Is n log n is greater than c1 multiplied by n power of 3 for all n greater than starting point, right? We have to prove this one. And how can we prove this one? I think is so much easier to say that this one is easy because we know that how can we ask the same question for theta notation, that how can we cut this and we transform it to n only in the form of n power of 3, because this one has n power of 3 and the right side also has n power of 3. We try to remove this equation. So what can I try to do is uh, n log n is greater than equal to 0. That what I can do for all n is greater than 1. If we look on this one graph again, we can see that um, for the x multiplied by logarithm of x, there will be some number that is negative, right? So we can, and at the starting point of 1, it will be 0, right? Because n equal to 1, log 1 base logarithm of 1 base 10 is 0, and 0 multiplied by 1 is 0, and it will be 2. And the logarithm will be increasing function for at the starting point of n equal to 1. You can see that the graph is increasing at point 1, except this for less than 1 and greater than 0 it can be decreasing, but for the starting point from 1 it will be always increasing. So we can write this, and we add both sides by n power of 3, and we write this n power of 3 and log n. We add both sides for this inequality, and it should be easy for to see that what is constant C1, right? It's 1, right? The right side will be n power of 3. So that means we can find the constant C1 and the starting point, so that this equation will be true because we have the same, right? In multiplicity, in log n, and the C1 will be 1. So we just simplify that. Choose C1 is equal to 1 and n0 is 1. That is the starting point. For the next is upper bound, right? For the upper bound, this is n power 3 n log n is greater than or equal to c to n power of 3. This is the hardest one at the same problem for lower bound of the first problem, because how can we cast this? Because we can use the sign n log n is greater than or equal to 0, because it is the greater or equal sign, but this one is less than or equal sign. So we can combine this expression to be only n power of 3. How can we prove this one? It's going to be the hard thing. But what I can do is, I think the easiest thing we can do is we just try to transform this n log n to be n power of 3. So because we know that n power of 3 is asymptotic, grow larger than n log n. What about we write this equation as n log n is less than or equal to 10 n power of 3. I try to um, do this one, so we can choose the small starting point. So we ask the same question, that what is the starting point so that make this inequality to be true. So we can see that if n is equal to 1, this one will be 1 times log 1, and if it will be 0, is less than or equal to 10 times 1, and we will 10, and it's true. And we can prove this for the other end, and we can try to prove some integer n, and we can say that, oh, this one will be always be true, that if it's starting from 1, so we can make the starting point of n is greater than or equal to 1, and say that n log n is greater than or equal to 10 of n probability for all n is greater than 1. This is the starting point, and we add both sides by n power of 3 to make this inequality equation to be the same as the top one. So we add both sides again, and we get this inequality equation, that is n power 3 plus n log n is greater than or equal to 11 of multiply n power 3. This is the constant C2, right? And this n power 3 is the same as gn function. This one is fn function, at the same equation. So we say that should constant C2 equal to 11 and n0 is 1. That is, and after that, we prove for upper bound and lower bound. We just write that, okay, we, we just we just write that we can choose blah blah blah, that is c1 is equal to 1, c2 equal to 11, and for the starting point for upper bound and lower bound is 1, so it's easy to have use the maximum one, that is 1, such that c1 times gn n power 3 is greater than or equal to n square n log n greater than or equal to c2n. And we can summary, since we prove that we can choose c1, c2, and the starting point n0, we can say that trust the n power 3 plus n log n equal to theta of n square n power 3 is true. Yeah, we can write this. Okay, so for the next one is number 4 is big O notation. So big O notation is the upper bound, right? Is the upper bound function for some function. It's the upper bound. So we can prove, right, the theta notation, but just prove just upper bound. So what we can do, we can do something like that. We can say that, oh, we want to prove that 3 log n base t part 5 is equal to big O of of log n base 2 or not, is true or not. We can write like this. And for the definition of big O notation, if you can remember, we can write that by definition, then x is c greater than 0, and some starting point that is greater than 0 is the same as theta notation, but only just upper bound. Like that, 3 log n base 3 part 5 is less than or equal to c of log n base 2. We have to find this constant c and the starting point, right? We have to find this one. So we are going to prove this one. So how can we prove this one? And since both two form of expression is not log n base 2, we will try to transform this one to log n base 2, and we can prove this one like the theta notation. So the technique that I will give you for the to prove something like big O notation or big theta notation or big omega notation, we can simply forget this equation and only remember the sign, and we will try to transform this equation to the right one, to log n base 2. Okay, we just want to prove that. So the easiest one is, because the sign is less than or equal to, right, we can write that, okay, how can I transform 5 to log n? So what I can do is, what can I do is, what about we we write 5 log n base 2 for all n greater than or equal to 2. We cannot use 1 because log 1 is always 0, and 5 will not be less than or equal to 0. So we can use n equal to 1. So we have to use n equal to 2 because the phi log 2 base 2 log 2 base 2 is 1. So it phi log 2 base 2 is 5. And phi is less than or equal to 5. And it is to equation inequality equation for n equal to 2. And where we can give another example, right? We can just okay, n equal to 4 is still true, n equal to 8 is still true because we use n equal to 2 equal to 4 equal to 8 because we can write this equation as 2 power of 2, 2 power of 3, and we can find the log the log the log logarithm easier, and we can prove it easier, and we can simplify that. Okay, for all n that is greater than or equal to 2, this inequality will always be true. And what about the next one is 3 log n? How can we prove this? I have to find the right side that is in the form of log n base 2 and some constant to make it easier for the starting point. So what I can do, we can see that for n equal to 2, log 2 base t is estimated at um we can just use n equal to 3. It will be easier for me. You can use n equal to 2 just but you just have to prove that this inequality will be true for some starting point. So for n equal to 3, log t base t is equal to 1, right? And we know that log 2 base log 3 base 2 is estimated as 1 point something. It's greater than 1, we know that. It's some floating point that is greater than 1. So if we can use this, I will just say that okay, I will use the some large large constant c that is greater than t. For safety, I can choose 5 or 6. And what for n? For n equal to 1, we can see that 0 is less than or equal to 0. For this one, it will be 3 times for n equal to 3. This one will be 3, and this one will be something that is 6 point something, right? That is greater than 6. So what we can write? We can write that 6 log t base 2 6. We can write like this. So and it be 2, and for another n from the starting point it will be 2. So we can say that okay, t log n base 3 is less than or equal to 6 log n base 2 for all n is greater than or equal to 2. Or you can use 1 also, but I just want the starting point to be consistent with the phi one. The phi log n base 2 we should starting point to 2, so we have the same starting point. And the next thing we can say that since 3 log n base 3 is less than equal to 6 log n base 2 and y is less than or equal to 5 times log n base 2 for all n is greater than or equal to 2, then we have two inequality equation and have the same sign less than or equal to. We can combine this combination, so we can say that okay, it's t log n base 3 plus 5 is less than or equal to 6 log n base 2 plus 5 log n base 2. And this is the fn function, right? Fn. If you don't forget, and it's t log n base t plus 5. This one can be combined as 11 log n base 2. So let me remind you that this one is Fn, this one is constant C, this one is Gn. It's the same as the definition of big O notation, and this is starting point. So we say that we can choose C equal to 11 and n 0 equal to 2, such that 3 log n where t plus 5 is less than or equal to c log n base 2 for all n is greater than or equal to n0. Thus, or therefore 3 log n where t plus 5 is equal to big O of log n base 2 is 2. That is the easiest thing we can do. And for the last question of proof asymptotic notation, this one I will tell you that we have to use some property of logarithm that we say that is x powered by logarithm of y is the same as y power of logarithm of x is the same thing. This is the important for this problem. And for omega proof method, we can use the same little. This is the little omega notation. It has more strict definition for big omega notation, and if in the opposite of little o notation, we can prove that if we have fn and n is nearly as infinity number, and we have fn divided by gn, this limit value it should have the value of infinity. If it is 2, we can summary that fn is omega of gn. It's the easiest one, and if you want to know the definition, I can go to that. So for the first method, we can say that okay, f we can fairly say that okay, we want to prove that n power of logarithm of x is equal to ln omega of 5 power of logarithmic of n is true or not. We want to prove that, and fn is n power, and we can show it by using limit equation, and gn is equal to 5 power of log n. So we can write this as limit n nearly as infinity. Fn is n power of log n, right? And the gn is 5 log n. And I can swap between n and 5, and it should be something like this. N power of log 5, and it just the degree of n, degree n. The n has a degree between log x and log 5, and let me ask you that between log x and log 5, when we use the limits, how can we know? For the example, if I have n squared and n, we know that oh, n squared is grow larger than n, it should be infinity because the power of 2 is greater than power of 1, right? And what about log x and log 5? We know that log x is greater than log 5. That means this limit will equal to infinity. Or we can write this as n log x at log 5. We can write this expression and it's equal to infinity, so we can simply that n power of log x is equal to little omega of 5 power of log n is true. And so for another form, for the second method, I don't know I can prove this one or not, but the definition of little omega, oh, I know that I forgot something. Go back to the problem that we have little o notation. Please don't forget that you specify this one. Okay? This definition will be important for little big O and big omega. And for theta also. So for the theta, we should specify that okay, it should not be 0 or negative. For the equation, we have to write this. I forget to write it, but it is not that important. But by the definition of notation, greater. It should be greater than 0. Okay. So go back to little omega notation. For little omega notation, it's just the opposite definition for little o notation. It is that for all c greater than 0, there exists some n 0 greater than 0 such that and we write 0 that it should be like this, and this one will be or we can write like this. Let me the fn is, it should be fn because the little omega is the lower bound of some function, the lower bound, the opposite of little o. Little o is upper bound, right? Little omega is lower bound. So fn it should be greater than lower bound, like c of gn, and cgn is greater than or 0 also. This is what is the definition of it, and we can, and if for all n greater than starting point. So what can we do about this equation? And write as the real one, that is fn is n power of log x, right? And g, the function gn is 5 power of log n greater than 0. We have to prove that there always exists in the starting point for all c, for all constant c. There exists some starting point that make this inequality to be true. So what we can do is we can rephrase. Let me rephrase this as n of log x is greater than cn log 5, right? So what we what we can write, we know that log x is greater than log 5, and here what can we continue? We will try to um, specify that, okay, we will try to specify, we will write in a form such that left the n alone. Again, n should be alone, no constancy involved. So what can we do? We can write that, okay, log x is greater than log 5, and we power of it, we know that by the definition of an exponential, n power of log 5 like this, and we will left this one to be easier to prove. What we can do, we can write that log 5 is greater than 1. So this one will greater than 1. So what about we write it as log x minus log 5 is greater than c. And we say that n is greater than c of log x minus log 5, and here we can leave n alone, right? Oh, and I forget to tell you that how can I rewrite this phase, because c is greater than 0, right? C is greater than 0, and n, and this one is greater than 1. And since c is greater than 0 and n power of this is greater than 1, we can show that, or we can use at the from the from this one we can write this and use this. So that means we we set the starting point to maximum of 1 when we choose C is the root, the floor of C log S minus log 5 plus 1. So we can say that we can away by n0 for all c's greater than 0. Thus, the little omega notation is true. That's what we can write. And that is the little o and little omega notation. For to prove the notation is it is pretty hard to write. So it's pretty hard to write. If you can use the definition, you can use the limit method, that the limit of fn divided by gn should be infinity for n is nearly as infinity number. You can use just this one if you don't want to prove that long for the little omega notation. And for little o notation, you must specify that limit of fn divided by gn for n is nearly as infinity should be equal to 0. And don't forget like me about the definition for little o notation or little theta omission, that for the definition you should specify this one. 0 is greater than this one. Don't forget to write it. It it can you can leave it alone, but it it should be great to write. All right, and that is for little o asymptotic notation for this one for today. Thank you for listening my practice of asymptotic notation proof. Thank you for today.